describe this kind of processes. Normally, the result is that the boron to carbon ratio is proportional to rigidity to some power. One of the model, Kolmogorov turbulence model, by Kolmogorov, based on turbulence of magnetic field, gives this power index of -1/3. And some other model gives different predictions. For example, this questioning theory leads to delta equals -half. So our measurement is this line that gives a boron to carbon ratio of -0.35. This is almost exactly what the Kolmogorov predicted, -1/3, and it's a very simple power law, simple line without much structure. And I have shown this already, that some models predict that there has to be some feature in order to explain the excess of positrons. The point is that positron and boron are both secondary particles. So whatever mechanism that produces extra positron should also have effect on the boron. For example, it will also create extra boron secondary particles, and like this model. And so with this kind of single power law, quite featureless, and with good agreement with the prediction, we have to ask how much room is left for a pure astrophysical explanation of the excess of positron. So this is really a very strong constraint to the possible explanation of positron from known sources. Okay, so based on this, I think we conclude that a simultaneous agreement between the model and the spectra of every element, proton, antiproton, helium, electron, positron, and lithium, beryllium, etc., up to iron, will provide a very, very strong constraint to the parameters and to the understanding of galactic environment, like interstellar material, magnetic field, the sources, etc. This is very, very important to have more and more spectrum, all these elements. And this exercise has already started, for example, in this paper. They have made predictions of many different models. And you see that it's another simple way to do it, simple task. For example, in this black line, it agrees with here, this is the electron spectrum. This is boron to carbon ratio. So the black line is again sort of okay for both cases. However, this black line is clearly not in agreement with data for the proton to helium ratio. And so this kind of study, we hope, with more and more data from AMS, will eventually lead to a much better understanding of the cosmic ray propagation. With that, then we can try to explain the excess of positron. So it is obvious that for the next step of AMS, we want to measure more spectrum. What comes next is most likely a lithium spectrum. This is a preliminary result, and we see that the lithium spectrum follows this kind of very soft spectrum. That's a signal that it's a secondary particle in the cosmic ray. And again, we see some kind of break of power index at about 300 GeV. All these features is to be explained by the model. And hopefully, eventually, we will extend all these measurements up to iron. So I come to my summary. Excess in positron and antiproton strongly suggests the existence of an unknown source However, we need to know the astrophysical sources with better precision. To correctly evaluate the positron antiproton from astrophysical origin, a precise cosmic ray acceleration and propagation model is needed. So AMS measurements of proton, helium, boron, and carbon spectra already provide very strong constraints to the existing cosmic ray models. But we intend to measure more elements up to iron now. And there are also several new features which are expected to be explained. For example, the spectral index break at about 200 GeV for many spectrons, and expected the proton to helium ratio that keeps on decreasing at higher energy. And positron, antiproton, and proton follows the same power law, but not electron. So this is again unexpected, but it's a measurement. So to resolve all these problems, all these issues, continuing taking data through the lifetime of ISS of AMS is very important and critical. For this, I have a comment, not actually a comment, AMS has recently gone through a DOE review chaired by Barry Barish, and in the conclusion or the review panel's report, it says here, it concludes that there is an obvious case to support operation through the 3-year period covered by this proposal. This is a 3-year proposal. But also they conclude that there is a strong case for support through 2024, the current expected operation lifetime of International Space Station. So this is, indicates that the AMS is strongly supported by the DOE to operate to tier 2024. Hopefully by that time we'll have very conclusive results for many of these measurements. So stay tuned.
Thank you very much for the very nice summary of the AMS results. Any questions?
You showed the comparison of the antiproton data with some theoretical curve. Is the comparison very sensitive to the mass of the chi?
For antiproton, it's not very sensitive. It's a very broad peak because antiproton is heavy, and the production of antiproton tends to spread out different energy.
So it does not imply the value of the mass of chi.
Yeah, I don't think it's very easy to imply the mass of chi. You see, the mass of chi comes as a cutoff of this bound. That at 1 TeV, this curve should merge with cosmic ray background. But this is very broad. The theoretical uncertainty is very big. Unless we can really pin down this to a very narrow band, this is a broad line compared to a broad, and you can predict. I don't think you can throw much.
I can comment about these anti-proton issues. Recently, we have done similar studies. Because MS2 reduced the error bar very much in the low mass regions. If one wants to find a background consistent with the MS2 B over C ratios and the anti-proton data, they can find the previous background fittings or new background fittings cannot fit the low mass regions. There is some excess in the low mass region around MChi, around say 70 GeV, which is 60 to 70 GeV, which could be consistent with the so-called galaxy center excess.
You mean there's some excess in this region?
In low mass regions.
Yeah.
Low energy regions.
Yeah, I think there are several publications point out these features. I have no comment.
I'd like to understand, for instance, on slide 15, I'd like to understand the ability to measure anisotropy by AMS, given that it's in a low Earth orbit in the Earth's magnetic field. What do you actually report as anisotropy, and how does that relate to something like anisotropy outside the solar system? Can you comment on that?
This measurement has to be done at the energy above, like about 20 or 30 GeV. Below that, there's a clear anisotropy due to Earth magnetic field. But above 30 GeV or so, there's no effect. So,
okay, and then
basically, this measurement is done at high energy.
Okay, and the relatively small anisotropy of a pulsar model is due to propagation between pulsar and the Earth?
Yeah, because this is a model, but because of, first of all, electron is light. It curves a lot in the galactic magnetic field. So this pulsar has to be very close to Earth to have any effect. So I think this is based on the closest pulsar. Assume that it's a big injection from the closest pulsar. So if the pulsar is a bit further away, and also if there's a distribution of the pulsars, this effect maybe cannot be seen.
Yeah, I think from your talk, you are trying to normalize your background in various observables. You want to tell us basically that to estimate your background in your signal region, you have all these other observables that constrain the models, and then you have to go back to the positron fraction to constrain the prediction and then be able to say what's happening. But to me, it looks difficult even from the previous slide. You don't have any normalization of your background close to the observable you're actually measuring. You are normal. It seems that you are normalizing your background in the very low mass region, and then when you have the, similar to what Sming said, when you have this maximum and then the turn over there, it doesn't seem that you can actually normalize your model. I mean, if you could normalize your model in a flat region, you understand what I'm saying? Then
I understand, but
I don't see how you can.
I give you this example that they actually predict such behavior.
This particular model, if you normalize it, then it's consistent with the data.
Yeah, of course, it's fit to the data.
It's fit to the data.
But they are able to fit the data but predict such behavior.
Yeah. But then you test
like,
it. But then it fails in the other observable.
It fails here. That's my point.
Yeah.
You have to have agreement to every other measurement. Well, of course, this model was made before we published this.
So if not, let's next. Next speaker is Professor Sasaki from Kyoto.